From the moment of its inception, the universe has been on a journey. It began with a bang, an explosion of energy and light so powerful that it birthed stars, galaxies, and everything we know. But what happens when the energy of that initial explosion fades? The universe as we understand it is not infinite. It had a beginning, and like all things, it will have an end. By studying the movement of galaxies and dark energy, scientists are piecing together the story of the universe's final chapters. One of the most groundbreaking discoveries in cosmology was the realization that the universe is not static. Since the Big Bang, galaxies have been moving away from each other, like dots on a balloon being inflated. In the late 1990s, astronomers discovered the expansion of the universe is accelerating. This discovery implied the existence of a mysterious force dubbed dark energy that counteracts gravity and drives the accelerated expansion. Dark energy is estimated to make up roughly 68% of the universe's total energy density. As the universe expands and galaxies drift further apart, the cosmos will grow colder and darker, eventually leading to what is known as the Big Freeze. The idea of a universe in motion is a relatively recent concept in human history. Hubble's observations of distant galaxies showed that they were not fixed in place but were in fact moving away from us. This observation, now known as Hubble's law, provided the first concrete evidence that the universe was expanding. Imagine the universe as the surface of an expanding balloon. As the balloon inflates, every point on its surface moves away from every other point. This realization gave rise to the Big Bang theory, which posits that the universe began from an incredibly hot, dense state and has been expanding and cooling ever since. The discovery of the universe's expansion was a monumental achievement, but it was just the beginning of the cosmological puzzle. In 1998, two independent teams of astronomers studying distant supernovae made a startling discovery. Their observations indicated that the expansion of the universe was not slowing down as expected, but was in fact accelerating. This mysterious force was dubbed dark energy, a fitting name given its elusive nature. Despite its elusiveness, scientists have been able to infer the existence and properties of dark energy through its effects on the expansion of the universe. The accelerating expansion of the universe, driven by the enigmatic force of dark energy, paints a picture of a future that is both awe-inspiring and somewhat unsettling. As the universe continues to expand, galaxies will drift farther apart, eventually becoming isolated islands in the vast cosmic ocean. Over unimaginable spans of time, this relentless expansion will have profound consequences for the universe as we know it. The formation of new stars will eventually cease as galaxies exhaust their reserves of gas and dust. In this scenario, known as the Big Freeze or heat death, the universe will continue to exist in a state of perpetual expansion and cooling, but it will be devoid of the energy and activity that characterize it today. In the grand cosmic ballet, where gravity and expansion are locked in an intricate dance, dark energy has emerged as the enigmatic choreographer. Its influence, subtle yet pervasive, is gradually shaping the destiny of the universe. Dark energy, as its name suggests, does not emit light or interact with it in any way that we can currently detect. Some theories suggest that it's an intrinsic property of space itself, a kind of cosmological constant that maintains a constant energy density even as space expands. Whatever its true nature, dark energy appears to be winning the cosmic tug-of-war, leading to a scenario where the universe's expansion not only continues but accelerates indefinitely. As dark energy continues its reign, the universe will embark on a slow, inexorable journey towards a state of maximum entropy, a fate often referred to as the Big Freeze or heat death. The first casualty of this cosmic cooling will be the formation of new stars. As galaxies drift farther apart, the vast clouds of gas and dust that serve as stellar nurseries will become increasingly diffuse. The stars that do exist will slowly but surely exhaust their nuclear fuel. As stars fade away, the universe will be left with a scattering of stellar remnants, white dwarfs, neutron stars, and black holes. In the cold, desolate expanse of the distant future, even the most enduring structures in the universe will eventually succumb to the relentless march of entropy. Black holes, once thought to be eternal prisons, will slowly evaporate through a process known as Hawking radiation. Over vast stretches of time, this trickle of Hawking radiation will gradually deplete the mass of even the most massive black holes, causing them to shrink and eventually vanish entirely. The time scale for this process is almost incomprehensibly long, far exceeding the current age of the universe. With the evaporation of the last black holes, the universe will be left in a state of maximum entropy, where all matter and energy are evenly distributed. The Big Freeze, with its slow, inexorable decline into darkness and cold, paints a rather bleak picture of the universe's fate. However, it's not the only possibility that scientists have considered. For a time, a competing theory known as the Big Crunch held sway, offering a dramatically different ending to the cosmic story. If the density of matter and energy in the universe is high enough, its gravitational pull could eventually halt the expansion and reverse it, pulling everything back together in a cosmic implosion. Just as the universe began with a bang, an incredibly hot, dense state, it would end in a similar state of extreme density and temperature, a cosmic echo of its fiery birth. If the Big Crunch were to occur, it would be a dramatic reversal of the universe's current trajectory, a cosmic U-turn on a grand scale. The first signs of this shift would be subtle, a gradual slowing of the expansion rate, barely perceptible over astronomical timescales. However, as gravity tightened its grip, the pace of change would accelerate, leading to a cascade of increasingly profound events. Galaxies, once drifting apart, would begin to draw closer together, their mutual gravitational attraction overcoming the outward push of space's expansion. Collisions between galaxies, once rare occurrences, would become commonplace, lighting up the cosmos with bursts of star formation and the violent deaths of stars caught in the gravitational maelstrom. The Big Crunch, if it were to occur, would culminate in an event of unimaginable density and temperature. A singularity where all matter and energy in the universe would be compressed into an infinitesimally small point, mirroring the conditions thought to have existed at the moment of the Big Bang. Some physicists have proposed that the Big Crunch might not be the end, but rather a new beginning, a cosmic reset button. In this scenario, known as the Big Bounce, the singularity at the end of the Big Crunch could give rise to another Big Bang, creating a new universe from the ashes of the old one. This idea of a cyclic universe, endlessly expanding and contracting, has a certain philosophical appeal. However, whether the laws of physics would actually allow for such a bounce remains an open question. The Big Freeze and the Big Crunch represent two dramatically different scenarios for the universe's demise. One is a gradual descent into darkness and cold, the other a fiery, cataclysmic implosion. However, there is a third possibility, the Big Rip. Dark energy, the mysterious force driving the universe's expansion, might grow stronger over time. It could act as anti-gravity, weakening the bonds holding matter together. Eventually, it would tear galaxies, stars, and even atoms apart. If dark energy were to increase without limit, the universe would reach a rip singularity, tearing the fabric of space-time apart. This cataclysmic event would mark the ultimate demise of the universe, a cosmic apocalypse leaving nothing untouched. Galaxies would drift apart as space expanded, accelerating over time. Galaxies would recede at increasing speeds, their light redshifted into oblivion. Dark energy's influence would grow stronger, affecting smaller scales. Clusters of galaxies would be torn apart, stars ripped from their orbits, hurtling into the intergalactic void. planetary systems scattered and destroyed. Even tightly bound structures, stars, planets and atoms would succumb to dark energy. Stars would explode, planets disintegrate and atoms ripped apart. A universe torn asunder. The final moments of the Big Rip would be a spectacle of unimaginable chaos. The fabric of space-time would be stretched and distorted, rippling and tearing like a sheet of paper caught in a whirlwind. At the Rip singularity, the expansion rate would become infinite and all distances would become meaningless. Time itself would cease to have any meaning, collapsing into a single, instantaneous moment of cosmic annihilation. Cosmic behemoths of the void. In the grand tapestry of the cosmos, black holes stand apart, enigmatic objects of immense power shrouded in darkness. They are cosmic sinkholes, regions of space-time where gravity's grip is so relentless that nothing, not even light itself, can escape. Black holes are born from the death throes of massive stars, remnants of stellar cores that have collapsed under their own gravity. Around this singularity lies the event horizon, a boundary of no return. Anything that crosses this threshold is destined to be consumed. Despite their association with darkness, black holes are not cosmic vacuum cleaners. Their gravitational influence, while immense, is finite. In fact, black holes play a crucial role in the evolution of galaxies. As we contemplate the universe's ultimate fate, these cosmic behemoths take on an even greater significance. What role might black holes play in the final act of the cosmic drama? Will they be the last survivors, outliving even the faintest glimmers of starlight? Or will they too eventually succumb to the relentless march of time and entropy? The slow fade of giants. Black holes were once thought to be immortal. In the 1970s, Stephen Hawking revealed they emit faint radiation. This is known as Hawking radiation. It arises from quantum mechanics. Virtual particles pop in and out of existence. At the event horizon, they can be separated. One falls in, the other escapes, reducing the black hole's mass. This process is slow but inevitable. Over eons, black holes will shrink and eventually evaporate, releasing their energy in a final burst of radiation. In the distant future, long after the last stars have burned out, black holes may become the dominant form of matter. These cosmic behemoths will stand as solitary sentinels, preserving within their event horizons the remnants of a bygone era. The cosmic background radiation will redshift to undetectable energies, temperatures will approach absolute zero, and the universe will become a dark, desolate expanse. Only the faint glow of Hawking radiation will remain. As black holes evaporate, they will release their energy back into the universe. The evaporation of the last black hole will mark the true end of an era. The human mind struggles to grasp the concept of a true ending. We yearn to know what lies beyond the horizon. But when it comes to the fate of the universe, our intuition falters. The end of the cosmos represents the annihilation of space-time. Can there be a beyond when existence unravels? It's a question that pushes the boundaries of physics and philosophy, forcing us to confront the limits of our knowledge and the mystery of existence. The idea of a cyclic universe, one that undergoes an endless cycle of expansion, contraction, and rebirth, has captivated thinkers for centuries. It offers a comforting sense of cosmic balance, a reassurance that even in the face of ultimate destruction, the potential for renewal remains. Could the end of our universe, whether by Big Freeze, Big Crunch, or Big Rip, simply be the prelude to a new beginning? Could the singularity that marks the end of space-time also be the seed for a new universe to blossom? If such a bounce were possible, it raises tantalizing questions about the nature of these cycles. The possibility of a cyclic cosmos, of a universe continually renewing itself, offers a glimmer of hope amidst the vastness and indifference of the cosmic expanse. The contemplation of the universe's ultimate fate, whether it be a slow fade into darkness or a cataclysmic rip in the fabric of space-time, can evoke a sense of existential vertigo. Faced with the immensity of time and space, our own lives can seem fleeting and insignificant. Yet there is also a strange beauty in this realization. The knowledge that our universe had a beginning and will eventually meet its end underscores the preciousness of our moment in time. It reminds us that we are part of something much grander than ourselves. The quest to understand the universe's fate is a deeply human endeavor. It's driven by our innate curiosity and desire to find meaning in the cosmos. The theories we've explored, the Big Freeze, the Big Crunch, the Big Rip, represent our best attempts to grapple with the ultimate fate of the universe. They are testaments to the power of human curiosity, our drive to understand the cosmos and our place within it. Each theory carries its own unique blend of awe and unsettling implications. Despite their differences, these theories highlight the vastness of the universe and the relative brevity of our own existence. Faced with the immensity of the cosmos and the profound mysteries it holds, it's easy to feel a sense of insignificance. Our planet, our civilization, even our entire species can seem utterly insignificant against the backdrop of billions of galaxies, each containing billions of stars. Yet, this perspective can also be incredibly liberating. It allows us to step outside of ourselves, to see our lives and our concerns from a cosmic perspective. It reminds us that we are part of something much grander than ourselves, a story that began billions of years ago and will continue long after we are gone. This realization can foster a sense of humility, a recognition that we are not the center of the universe, but rather fortunate participants in a grand cosmic drama. The study of the universe's end, far from being a morbid fascination, can actually be a source of profound inspiration. It reminds us that even in the face of ultimate destruction, there is beauty, there is wonder, and there is the enduring power of the human spirit to seek answers to the universe's most profound questions. The universe, in its vastness and indifference, may not care about our fate, but we care. We care because we are creatures of consciousness, capable of contemplating our own existence, driven by a need to understand, to find meaning in a universe that often seems devoid of it. Our quest to understand, to unravel its secrets, will continue as long as there are minds to ponder the cosmos. Hit that subscribe button for more content.